Recall that we had this differential equation that came from a spring mass system, where you have some object of mass m at the end of a spring, where the spring has some stiffness, k, and some damping coefficient, gamma. So k represents a proportionality constant that comes along with Hooke's law, and gamma represents a crude model for friction, energy loss due to friction in the spring. Then our differential equation was Newton's second law, mass times acceleration. So here x represents the displacement from equilibrium. So let's say this is the natural position that the spring wants to be in, and we'll call that x equals 0, and then we choose a direction, like maybe this way is positive x, and x represents the distance that the mass is displaced from equilibrium. Then Newton's second law says mass times acceleration equals the sum of the forces. The force due to Hooke's law, due to the the restoring force of the spring, is this, negative kx, and then the damping force was negative gamma x prime. So here m, k, and gamma are all positive. Well, non-negative. I guess mass is positive, k is positive, and gamma is allowed to be 0. When gamma is 0, that's when you have no damping. Okay, then we rearranged this to look like this. And we also got a similar kind of differential equation for RLC circuits. But those are pretty much the same thing, just with the m and the gamma and the k replaced by other things having to do with circuit components, and with x replaced by something having to do with circuits. So let's analyze this and figure out what we can figure out about it, and then whatever results we get, we can just translate them over to the RLC circuit or any other differential equation that looks like this, which is apparently a lot of them. Okay, so now with all the stuff that you saw in the past few lectures, we are equipped to fully solve this problem in general, to figure out the general solution to this and be able to solve any initial value problem. So by initial value problem, I mean a situation where you're told, in addition to the differential equation, so in addition to mass and these coefficients, you're also told an initial displacement. So for example, this could be 0 if the, at time 0, the thing is at equilibrium, or it could be something non-zero, like 7, if you, at time 0, initially someone has stretched the mass 7 units of distance away from equilibrium. So this is like, how far out does it start stretched? And then x prime of 0 equals, and then some choice of v naught. So this would be 0 if you just like held it outstretched and then let go. So you released it from rest, released it while it was initially not moving at all. Then the initial velocity would be 0. But if you gave it a kick, so maybe if you stretched it by a certain amount, x naught, and then after you stretched it, instead of just letting go, you gave it a kick, or you gave it a push, then you would be granting it an initial velocity. Well, I guess, it takes time for you to finish pushing. So I guess when this differential equation starts to hold is when you are done pushing and there are no external forces on the system. There's only the restoring force of the spring and the damping force. Okay, so this is what I mean by initial value problem. We should be able to solve these. So our goal is to be able to solve this for arbitrary x naught and v naught. To be able to solve this all the time, our goal is to have a general solution. So we want a general solution to this. Okay, so we have a general method that always works now, and that's to start by guessing x equals e to the lambda t. And we plug in the guess, and we get a characteristic polynomial, m lambda squared plus gamma lambda plus k equals 0. Now, we need to find the roots of this polynomial, right? So right now there are not numbers here, they're variables. So how can I factor this? I mean, you can by completing the square, but effectively, if you do that, the roots you find are going to be the roots that come from the quadratic formula. That's where the quadratic formula comes from anyway. So let's see, lambda is negative gamma plus or minus the square root of gamma squared minus 4m k all over 2m. And maybe a nicer way of writing that is negative gamma over 2m plus or minus, I don't know, let's stick the 2m inside the square root. Somehow that feels better to me. I don't know if it's nicer, but it's at least an alternative way of writing it. So gamma squared over, so when I stick the 2m inside the square root, the 1 over 2m, when it goes inside the square root, it becomes 1 over 4m squared. So 4m over 4m squared, that's just 1 over m. Okay, yeah, I don't know which one I prefer, but in any case, what do we do next? So it depends on which case we ended up in, right? Either we have two either we have two distinct real roots here, or we actually only got one root, or we have complex roots, no real roots. So what determines which situation we are in? Well, it depends on what's under the square root here, right? If the thing under the square root is strictly positive, then we are in case 1. So if gamma squared, let's say, is greater than 4mk, then we are in case 1. We have distinct real roots. Distinct real roots. If gamma squared equals 4mk, and if gamma squared is less than 4mk, those are the other two cases. So if it equals 4mk, then this is just 0, right? And actually lambda is just, we only got one lambda here, right? It's just negative gamma over 2m. So here we only got one root. So this is case 1, this is case 2, and this is case 3. Case 3 is where we have complex roots. So let's write that out more carefully. So in case 3 we got, so this is if gamma squared is less than 4mk. That's the same as saying yeah, I don't know if I like this way of writing it. Maybe I'll stick with this. So if gamma squared is less than 4mk, then let me make some room to work this out over here. If gamma squared is less than 4mk, then lambda is negative gamma over 2m. So I'm copying from over here. Plus or minus. Then look at it like this. The square root of negative 4mk minus gamma squared. So you see I just, also 1 over 2m. So I just rewrote this basically, and I just put a minus sign and also flipped around the subtraction here. So this is definitely correct, right? Okay, just cleaned up the way it looks. So the reason I'm writing it like this is that this portion here is now positive. So this is, if we're in case 3, if this is happening, if this is true, then this here is positive. So I could rewrite this like so. Pulling out a square root negative 1, so pulling out an I And then here I have the square root of a strictly positive number, 4mk minus gamma squared. So you see I've got this real part, and this, let me circle it in a color. This is the real part here of the root, and this is the imaginary part. And both are real numbers, as they should be. So this is a real number because we've got square root of a strictly positive number. Okay, so this is what we'll have to deal with in case 3. But let's first look at the easy cases, case 1 and 2. So if we're in case 1, then here's our general solution. X of t equals c1 times e to the, and then one of our real roots times t, plus c2 times e to the, and then the other real root times t. So then I just have to copy over what the roots are. So in case 1, where this is true, what's under the square root here is positive, so these are just two real numbers, one that has a plus and one that has a minus. So I've got negative gamma plus square root gamma squared minus 4m gamma over 2m, and negative gamma minus square root of gamma squared minus 4m gamma all over 2m. So that's the general solution. That's victory right there. And let's look at the other cases, but actually first I want to get some insight as to what is happening. So, well, let me just fill in the other case. Then let's think about insight. Then let's look at case 3 afterwards. So in case 2, we have c1, e to the, and then our single root that we got, plus c2 t e to, and then that same root. So I just have to go and figure out what is the single root that we got. Well, if gamma squared equals 4mk, so this part is 0, then our single root is negative gamma over 2m, right? This part just vanishes. So here I just have negative gamma over 2m. Negative gamma over 2m. Okay, and then we'll look at case 3 in a moment. But clearly what you're going to have in case 3 is some oscillation happening, right? Because of the complex roots. That's what always happens. Okay, so what's going on in case 1? I've got without even plotting anything, I do have a way of interpreting what's going on, which is I have an exponential, and I know what exponentials look like. They can look like one of two very different things, either exponential growth or exponential decay. So either I have exponential growth in time for this term, or exponential decay as time goes on. Which one is it, growth or decay? Well, to figure that out, I just need to look at whether this number is positive or negative. If it's negative, then I'm looking at decay. If it's positive, I'm looking at growth. Physically, what would you expect? Just what would you guess physically? Probably that it's decay, right? You wouldn't expect x of t to possibly just grow, for the mass to just fly off the spring, to just fly off the equilibrium position forever for no reason. That's kind of random, right? Probably it's exponential decay. And exponential decay is always towards 0. So just physically, we expect both of these to be decay terms, so that no matter what C1 and C2 are, no matter what the initial conditions were, x of t will always go to 0 as t goes on. So both of these terms decay. That's what you expect. But do we see that if we look at the sign of this exponential rate here? Is it really negative? Well, so I've got negative gamma minus a negative, so okay, yeah, so there's two of them. There's one that has a plus and one that has a minus, right? The one that has a minus, that's definitely negative. Like negative gamma minus square root of whatever. Negative gamma minus a positive number, that's going to be negative for sure. So no doubt about, sorry, I keep flipping to the wrong page. No doubt about this one, that's decay, negative gamma minus something. But negative gamma plus, that one seems like it depends. So if you look at just the plus here, negative gamma plus this, is that necessarily negative? Or could some choices of m and k and gamma make it positive, maybe? Well, think about it this way. What you've got, okay, so let me pose the question in a more clear way. Okay, there, this is what I'm asking. Oh, sorry, with a negative gamma. Is negative gamma plus this necessarily negative? So here I've got negative gamma, and then I'm adding something which might be large enough to make this to make the whole thing become positive, right? But that cannot be. This will never be so large that in magnitude it'll be larger than gamma. That's because it's the square root of gamma squared minus something. So that's, I don't know if that argument feels right to you, but if it doesn't, then here's why I claim that this thing is necessarily bigger than, or is necessarily smaller than gamma. I think this is true because if you square both sides, this is true, right? Gamma squared minus something positive is going to be less than gamma squared. And, you know, if this, really the implication we need is if this is true, then this is true, taking the square root of both sides. So the answer here is yes, for sure. This is necessarily negative, always. So no matter what, we're looking at exponential decay on both terms, even the one that has the plus here, because this rate here is negative. Okay, so that's what's happening in case 1. You get exponential decay. In case 2, the rates here are definitely negative also, but you've got this being multiplied by t, right? But, I mean, yeah, sure, t grows linearly, but you're also multiplying it by something that decays exponentially. And eventually, if you let time run for long enough, exponential decay is going to beat out linear growth. Exponential decay is going to cause the term as a whole to decay towards 0. So in case 2, in this situation where the thing under the square root was exactly 0, so that's kind of a rare case, right? But in that rare case, we end up with, it seems, also decay towards 0, except one of the two terms is not pure exponential decay. It's exponential decay times linear growth, which is just like one step away from being pure exponential decay. Okay, and then in case 3, we're going to get oscillation. So I haven't written exactly what happens, but we get some kind of oscillation. Now these have names, and the motivation for the names is what causes us to enter into different cases, or one way of looking at what causes us to enter into different cases. Case 1 has big gamma, right? If gamma's big enough, then you get distinct real roots, and you have this pure exponential decay situation. This is like, in case 3, you have small gamma, right? If gamma is small enough, if the damping is small enough. For example, if there is no damping, if gamma is 0, then you're in case 3. Then you get oscillation. So case 1 is called the overdamped case. Or you say this is an overdamped oscillator. So this system as a whole, the system that we're looking at here, This is called a damped harmonic oscillator. An overdamped harmonic oscillator is one where specifically you have this inequality holding. That's overdamping. The damping is so large that there are no oscillations. The oscillation is snuffed out by the damping. There's so much friction in the spring that if you were to stretch the spring and then let go of it, it wouldn't oscillate and go whoa, 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 whoa. No, it would just, you would stretch it, let go, and then it would just decay back to equilibrium. That's it. It wouldn't get a chance to oscillate because it's so heavily damped. That's overdamping. Can you guess what this one is called? Underdamping. So that's small gamma. There's not so much damping that it snuffs out the oscillation. The oscillation is still allowed. And then in the middle, this is not like a realistic case because it requires gamma to be a perfect, exact, certain number, right? But so let me call it perfectly in between gamma. And that is called critical damping. Okay, to really get a feel for what is happening in all these different cases, I think we should look at some plots. So let's do that in the next video.